One use of primitive roots concerns the decimal expansion of a fraction. In general, the decimal expansion will be a sum of fractions whose denominators are powers of 10 and whose numerators are between 0 and 9, which sounds suspiciously like it has a connection with mod n arithmetic. In some cases, our decimal expansion is terminating. On the other hand, in some cases, we get a repeating decimal. The minimal repeating part is called a repetend, and we usually indicate it with a bar. So 0.3 repeating is going to be written this way. Can we predict how many digits are in the repetend? Let's start with unit fractions with prime denominators. Suppose the expansion of 1 over p has an n-digit repetend. So we go through the first n decimal digits, and then we repeat them in the next set of places. So let r be this first terminating part, the repetend itself, and so we can rewrite our fraction as, and factoring out r, and we have this geometric series which we can write in closed form, and do a little algebra, and do a little more algebra. And if we reduce mod p, we get, and so 10 to the n is congruent to 1 mod p. Well, we can't really do this because r isn't an integer, and so we can't go from an equality to a congruence without addressing that problem. But if we could, this suggests that there is a relationship between the order of 10 mod p and the decimal expansion of 1 over p. Now remember, concrete doesn't hurt. Let's try a couple of specific examples. Let's find the order of 10 mod 3, 7, and 11, and compare with the decimal expansions of 1/3, 1/7, and 1/11. So note that 10 is congruent to 1 mod 3, so 10 has order 1 mod 3, and 1/3 has a 1-digit repetend. 10 is congruent to 3 mod 7, and 3 has order 6 mod 7, and 1/7 has a 6-digit repetend. 10 is actually an element of mod 11, so 10 squared is congruent to 1 mod 11, so 10 has order 2 mod 11, and we find that 1/11 has a 2-digit repetend. This suggests that the order of 10 mod p gives the number of digits in the base 10 expansion of 1 over p. Let's try to prove this. Note that this would be an if and only if statement. If 10 has order k mod p, then the base 10 expansion of 1 over p has a repetend with k digits, and if the base 10 expansion of 1 over p has k digits, then 10 has order k mod p. Let's start with the second and assume the base 10 expansion of 1 over p has a repetend of k digits. We find the decimal expansion by computing 1 divided by p. If the repetend has k digits, this is the same as saying that k is the least value for which 10 to the k divided by p has remainder 1. For example, for 1/3, if we divide 10 by 3, we get remainder 1. Or for 1/11, if we divide 100 by 11, we get 9 with remainder 1. And for something like 1/37, if we divide 1000 by 37, we get a number with remainder 1. And so this also means that 10 to the power k is congruent to 1 mod p. And so we have our theorem. If the decimal expansion of 1 over p has a k-digit repetend, then 10 will have order k mod p. Now suppose 10 has order k mod p. Then k is the least value for which 10 to the power k is congruent to 1 mod p. Consequently, 10 to the k divided by p, we can rewrite that as our whole number quotient n plus 1 over p, because 1 is our remainder. And so if we divide through by 10 to the k, we get this first term, which is our n-digit repetend, and then we get this remaining term. And note that that remaining term looks like, factoring out of 1 over 10 to the k, we get n over 10 to the k. Well, that's our n-digit repetent again, plus another copy of 1 over p times 1 over 10 to the k. And so our next term will give us another n-digit repetent, and so on to infinity. And so if 10 has order k mod p, then the decimal expansion of 1 over p will have a k-digit repetent. So what if p isn't prime? We can still find the order of 10 mod p, as long as the greatest common divisor of 10 and p is 1. So let's try to predict the number of digits in the repetent of 1/9, then verify by direct computation. So note that 10 is congruent to 1 mod 9, so 10 already has order 1, so we predict the repetent of 1/9 will have 1 digit, and we confirm that it in fact does. What about something like 1/21? So let's start by finding phi of 21, which will be so 10 will have order that's a divisor of 12, and so the possible orders of 10 will be, we find that 10 actually has order 6 mod 21, so the repetent should have 6 digits, and we find it does. Note that if 1 over p has a k-digit repetent, then q over p will also have a k-digit repetent. So let's suppose that 10 has order k mod p, so 10 to the k is congruent to 1 mod p. Well, if I multiply that by q, and what this means is that after finding k partial quotients, our partial remainder is once again q. And you might consider why this doesn't work if the greatest common divisor isn't 1, if our fractions haven't been reduced to lowest terms. So let's try and predict the number of digits in the repetent of 3/7 and verify by direct computation. So we see that 10 has order 6 mod 7, and so 3/7 will have a 6-digit repetent. What if p is composite, but the greatest common divisor of p and 10 is greater than 1? Well, this would occur if p has factors of 2 and 5, where the remaining factors will be relatively prime to 10. So we could write 1 over p as this 1 over 2 to the I of 5 to the j times 1 over q, and since this first factor is a terminating decimal, the net effect is the same as multiplying a non-terminating decimal by some number n. And so we have our general theorem, let p be a product of 2's, 5's, and other things relatively prime to 10, and suppose 10 has order k mod q. The decimal expansion of 1 over p will have a k-digit repetent. So let's predict and verify the repetent of the decimal expansion of 1/75. We know that 75 is 25 times 3, and 3 has a 1-digit repetent, and when we compute 1/75, we get where the 3 is repeated.